Chapter 4, Section 2, Atomic Structure. Subatomic particles make up the bulk of an atom. Subatomic just means lower or smaller than an atom. There are protons and electrons that have an electrical charge. Protons have a positive charge. Neutrons have no charge. They are neutral, which is one of the reasons that made them the last subatomic particle to be discovered. And electrons have a negative charge. The nucleus of an atom makes up 99.99% of the mass of the atom, but the nucleus is 1/100,000th the volume of an atom. The volume is determined by the electron cloud. Since subatomic particles are so small, they can't be measured in grams or even micrograms. They are measured in what we call atomic mass units, or AMU. 1 AMU is equal to 1.61 times 10 to the negative 24 grams. So if you remember when we learned about scientific notation, that negative 24 means that this is a very, very small number. It looks like this. So again, we use scientific notation to get rid of those zeros to make this a little more manageable. 1 gram is about the mass of a paperclip. So this much of a paperclip. So in this chart, you can see we have organized the different subatomic particles that we know of. There are protons. Their symbol is a P with a little plus sign. They have a positive charge. They're located in the nucleus, and they have a mass of 1 AMU, or 1.67 times 10 to the negative 27. Also in the nucleus are neutrons. They have no charge. They're neutral, so we've just put the N with a 0 next to it. And they also have the same mass as a positive proton. Next, we have electrons. They're not found in the nucleus. They are found outside in the electron shell. They have a negative charge. And this right here, that E with the little negative sign, you're going to see that. That's very common. And they have a 0.0006 AMU, or 9.11 times 10 to the negative 31. So what you really need to know is that neutrons and protons have the same size. Protons are positive, neutrons are neutral, and electrons are a fraction of the size of these guys, and they have a negative charge. Now, what makes up protons, neutrons, and electrons? Well, we're not really for sure, but scientists are fairly certain that they are made up of what we call quarks or flavors. And we have different types. There's up, down, strange, charm, bottom, and top, and they combine to form hadrons. The most stable of these hadrons are the protons and the neutrons. So when we look at our electron configuration, or our electrons, where are they located? Well, this inner circle represents our nucleus, and this is where you find all of the protons and neutrons. The first cloud level, this or energy level, can hold a maximum of 2 electrons. Because remember, if this nucleus is positive and our electrons are negative, they're attracted to one another. But those 2 electrons are actually going to be repelled by one another. So they have to find that delicate balance of being close to the nucleus, but far enough away from the other one. Then our next energy level holds up to 8 electrons, and they're distributed over 4 different shaped orbitals. The same thing with the third energy level. We can hold up to 8 electrons, so a maximum of 18, and they're distributed over 9 orbitals. So the concept of electrons, they're going to fill those energy levels around the nucleus. The orbitals are just the region in which the electrons are likely to be found. Orbitals, clouds, they're kind of the same thing. Each level only holds so many electrons. Whatever that outermost electron level is, we call that the valence. That is just the outermost level. So the valence electrons are the ones that are in the outermost shell or level. The reason that that's important is because when we start talking about how atoms combine with each other, this is actually where chemical bonds happen. They happen with those outermost shells. There are 4 types of orbitals. There's S, P, D, and F. We're not going to go too much into it. The ones that you really need to worry about are S's and P's for this class. If you go on to take more chemistry classes, you may get into some of the d orbitals, but that's just how they're arranged. And then we talk about electron configurations. So vanadium, which is right here on the periodic table. It has 1s2, 2s2, 2p6, 3s2. So that just tells me that my s orbitals are full. I have one row of the p orbital that's full. And then my s orbital down here, so that sp, d, and f, my s orbital down here in the third row is filled all the way up to the second shell. Atomic number. When we read the periodic table, this is what we're looking for. There's going to be a symbol somewhere. It's always going to consist of at least one capital letter. If there's a second letter, it's always lowercase. And that's very important because we have a lot of elements that can be easily confused. Somewhere in the boxes, you're going to find the atomic number, which is also the number of protons, which is pretty handy. And then you're also going to see an atomic mass, that 4.003 for helium, is written in AMU. The atomic number tells us how many protons you find in the nucleus. It's kind of like, I like to give it the example, it's like your social security number. No one else is going to ever have that number. If that number changes, the person's identity changes. And we know that we can't change the identity of these atoms. They are what they are. So helium will always be helium. So the number of protons is found in the nucleus, and that tells you the number of the protons that are found in the periodic table. And this is going to be important when we look at the organization. The number of protons is unique. It never changes. In a neutral atom, so meaning it has no charge, it's not an isotope, in a neutral atom, the number of protons is going to tell us how many electrons there are and how many neutrons there are. So there's not going to be an overall charge with that atom. So for this one, there are 2 protons, which have positive charges, and there are 2 there's 2 electrons. We're talking about the charge here, so there's no charge here. The 2 electrons balance out the 2 protons, so the overall charge of a helium atom is 0. Now, the atomic mass is the total mass of all atoms' components. The mass number is the total number of neutrons and protons in an atom. You subtract the atomic number from the atomic mass to find that number of neutrons. The number of neutrons in an atom can change, which means that the atomic mass can change. You're only going to know that if you look at the atomic mass, find that mass number, and you subtract the atomic number from it. So if you have 16 for oxygen, you know that the atomic number of oxygen is 8. It'll always be 8. You take 8 away from 16 and you're left with 8. That means you have 8 neutrons. So let's look at some examples. This is Si. This number 14 right here is going to be my atomic number, and this is going to be my mass. So with this, silicon has an atomic number of 14, which tells me I have 14 protons. I have 14 neutrons and 14 electrons because there is no charge indicated here. If you were told that it had a charge, then you could figure that out, and we'll get to that later on. Fluorine has an atomic number of 9, which means we have 9 protons and 9 electrons. But because that mass number is 19, we're going to take 19 minus 9 and we're left with 10. So that means we have 10 neutrons. So in one way, shape, or form, whether it's on the periodic table like this, or you're just told this is how many neutrons you have, you're going to be able to figure this out. You don't have to guess. And another thing I want you to notice, these are all whole numbers. We don't deal with fractions. We don't deal with decimals when we're talking about numbers of protons, neutrons, and electrons. So here we have lithium. The atomic number is 3, which means we have 3 protons. The mass number, we're told, is 7. Right here, we're told that it's 7. So that means that the number of neutrons is 4, because 4 plus 3 is 7. Now, it's not a positively, negatively charged atom, so we assume that the number of protons and electrons is the same. And then finally, atomic number of 90 with a mass of 232. It's a very large atom. Protons are 90, electrons are 90, because we've not been told anything different. You get that neutron number by subtracting the atomic number from the atomic mass. and that gives you the number of neutrons. So when we change the number of neutrons, that's what you call an isotope. So isotopes are atoms of the same element that just have a different number of neutrons. Therefore, they just have a different mass. It doesn't do anything to the overall charges. Now, carbon, for example, has a couple different isotopes. There's carbon 12, carbon 13, carbon 14. There's normally 1 to 2 stable isotopes for an element, and the atomic mass of the most common isotope is the one that's listed in your periodic table. That's how we get those decimals, is because we take into consideration these isotopes. All of those other forms of whatever element we're talking about are unstable. So like carbon 14, it's unstable. And they are going to fall apart through radioactive decay. And that's how we can actually determine the age of some very, very old things. When we represent isotopes, you may see it like this. You may see it like this. This is the most common form that I will give you. This just tells you this is carbon because that's the chemical symbol for it. That's what you find on the periodic table. And the number after it tells you it's not a typical, this is going to be an isotope. So isotopes have the same chemical and physical properties. They can be represented in a number of ways called isotope notation. Element symbols or names with atomic masses both give us that same information, just looks a little different. The element symbol with atomic number and atomic mass. So we know that carbon has an atomic number of 6. That means it has 6 protons. But because it's telling us that mass number is 14, that means we must have 8 neutrons. So this is what they would look like, the isotopes of carbon. This is your typical carbon 12. This is the normal variety of carbon. 6 protons, 6 neutrons, 6 electrons. Notice that first shell only has 2 electrons in it, and then it spills over and fills the rest. So there are 6 of those electrons. Here we have carbon 13. You can see there's 6 protons, 6 electrons still, but now we have 7 neutrons. And here's carbon 14 with that very unstable nucleus, 6 protons and 8 neutrons. Think of it as like a cake, like a big, tall layer cake that doesn't have any internal supports. The bigger it is and the more off-center it is, the more likely it is to fall apart. And so this atom is more likely to experience radioactive decay.